So let's now think about a quick summary of some of the basic concepts in reinforcement learning. In particular, let's talk about return, state value, transition probability, and reward. So we've thought in terms of an agent interacting with its environment, and this is often depicted in this kind of interaction schematic. We have an agent which can observe the state of its relationship with the environment, and on the basis of the state, it can take an action AT at time step t. This in general will move its relationship with the environment, so it moves to a different state, st+1. It may or may not get a reward, but we will represent that by the reward it gets at rt+1. And the agent is then able to use this information to make its next decision. So overall then, at step t, the agent will observe a state. It will generate an action from one of the ones it can. It will get a reward from the environment, which could always be 0, it could even be negative. And in general, it will transition to another state as well. Now let's think about the policy of the agent, and that's written in terms of this symbol pi, and it's a distribution basically, pi a given t, so it's basically representing the probability distribution over actions given the state. So in a discrete task, such as moving in a maze, we might have north, south, east and west as 4 possible actions. And in that case, if we have a stochastic policy, when we specify the state, we'll get the probability for each of those actions occurring. And it could also be one of those action probabilities is 1, in which case it becomes a deterministic policy. Another important concept is the return g of t, and it is the accumulated future return or future reward that we actually want the agent to maximize as a general principle. So we can think of what's coming in the future as then being the cumulative future reward g of t in terms of the reward it gets at each step as it moves into the future. If we don't put a scaling factor on in front of these future rewards, however, there's a danger that if the agent is doing a task and it doesn't ever terminate, that we'll end up with a g of t which goes to infinity. And of course we can represent this sum written out here in a more compact form with a sigma representation. Generally, therefore, in order to avoid the problem of sequences going on forever and reward or cumulative future reward g of t going to infinity, what we can do is we can discount future rewards by a certain amount. And generally what we can do is we can put a scaling factor, gamma, in front of each reward. And as we go further into the future, what we do is we raise the power of gamma up by another step. So the immediate reward is basically gamma to the 0, which is 1. Then the second value is gamma to the 1, which is gamma. And then third one is gamma squared, and so on. And if we choose a gamma between 0 and 1, you can see that as we move further into the future, we discount more and more and more. Therefore, this sum will actually be finite rather than going to infinity, even if it doesn't terminate. So that's got that advantage. It's also got the other advantage that we weight more importance on things which happen closer to the present rather than things a long way away. So it cares more about things which happen quickly rather than things that happen a long way in the future. So state value is an important aspect of a system that represents the value of the state that we're in. So if we are in the state S, we want to know the value. And of course, the value will also depend on the policy, because depending on the policy, we'll be doing different things, and it'll get to its end goal in different ways. So that will also have an effect. We could also write down the expectation, if you like, of the cumulative future reward G of L, and take the expectation of that in order to get the value function. So this expression here is basically saying what we're going to do is here is the expected future reward g of t at a particular state s, and we take the expectation of that, and then that gives us the value of that state under the policy pi that we're doing. So that's why the pi comes into this expression as well. So value function therefore tells us how good a state is. It's indicative of the predicted future reward, but it depends also on the policy. And we saw as a very simple illustration of what a simple value function might look like was in terms of this game of golf, where we're just saying that we've divided the world up into these regions, and the closer we are to the hole, if you're on the if you're in the hole, you get 0, you don't get a negative value. Further away we go, the less reward or the less value that state is. So transition functions then is a way of modelling when we're in one state and take an action, what state do we end up in? So it's a model of the environment, and it indicates how we can move between states. And we can also put, if we wish, reward into such an expression. This is a conditional probability. So in this case, this is the conditional probability of the next of state prime and reward r, given we're in state S and take action A. We know that we can marginalise things out, though. This is something that we will do quite a bit. If we have let's say we had a discrete joint probability P A and B, we know that if we want to get rid of the effect of B and just care about the probability of A, what we can do is we can sum the joint probability up over all values of B, and that will effectively just give us the marginal probability of A. And we can do exactly the same thing for this expression for the transition function. So probability of state S prime and reward given the state we're in and the action we take. We can marginalise, if we wish, across all rewards and get rid of the reward term in this conditional probability. So now, if we sum across all rewards, we can end up with a probability that we're in a future state S prime given the current state and the action, and there's no term in there anymore with reward in there. So if we've got this state probability, state transition probability S prime given S and A, basically it's telling us if we start in state S and take action A, we'll end up in state S prime with the specified probability distribution, right? So that's what it's telling us. It's telling us this is a conditional probability. We'll be in new state S prime with a certain probability given we are currently in state S and we took action A, right? So it predicts the next state's probability, right? And if we've got, let's say we had 4 possible states that we can transition to, what this could potentially do is tell us what the probability of all of these is. It's giving us in that case, it would give us a discrete probability distribution telling us the likelihood of being in any one of those states. So reward function then, if we remember, is something we gain from making an action from a certain state into another one. And one example of that would be when we're in a maze and we finally get to the goal state. And this is generally given a positive reward, or at least not a negative reward. And we can write that down then as the expected value of, if you like, the reward we get given we're in state S and we take action A. So if we were in state 3 here, for that particular state, what we'd see would be we can get a reward if we're in state 3 if we take an action to move up to the goal state. So that the action would be moving up in that particular case. So we can think of this again then, that we're in state S and we take action A. We'll end up in state S prime, and we'll generally get an expected value of reward, which So basically, we're going to get expected value of reward given that we were in state S. We now move to state S prime, and we took action A. Right. So that's the expectation of the new reward, given we are in the current state S, given we end up in S prime when we take action A. So our S comma A predicts the next immediate reward that we get.